Give everyone a couple of minutes just to get their seats and get ready. So it's my pleasure to welcome everyone here tonight to PIANC A&NZ Northern Chapter's seminar on offshore wind and ocean energy. I've been looking forward to this event for quite a while now. My name's Jack Kleiner and I'm the treasurer for PIANC and also an engineer, maritime engineer at Oricon, and it's my pleasure to be emceeing this evening's presentations. It's great to have such a broad range of individuals in the room tonight, and also for those listening along, we have a whole bunch of consultants, researchers, engineers from the public sector, and of course the students that are also here with us tonight. It's great to see you. I'd like to start by paying my respects to the traditional custodians of the land that we're meeting on here today, and pay my respects to the elders past, present, and emerging. For this evening's schedule, I'll just give you an overview of what we're going to talk about. So first of all, I'll introduce Sam, the chair of the Northern Chapter, to introduce PIANC, the organisation which has organised this in conjunction with the University of Queensland. And then we'll go through the three presentations from Professor Tom Baldock, Dr. Remo Kosu, and then Tara Kennedy. And then after that, we'll go over to the Advanced Engineering building down the road and have our networking part of the event. If everyone could please hold off their questions until after the individual presentations. We'll have a time after each presentation to ask any questions you may have. So without further ado, it's my pleasure to introduce the chair of the PIANC Northern Chapter, Dr. Sam Mazahiri. Sam is a structural integrity and maritime asset specialist who's been leading this chapter for 2 years now and has over 30 years of experience in key areas of mining, ports and terminals and transportation. Sam has authored over 100 peer-reviewed articles on a range of topics, including structural engineering, fluid structure interaction, and various coastal engineering topics. Currently, Sam is a principal engineer with the Dalrymple Bay Coal Terminal and concurrently holds key positions in organisations including Engineers Australia, Ports Australia, and Standards Australia. Please welcome him.
Thanks. Thanks, Jack, for the nice introduction. Hi, everybody. Thank you for coming along. I'm trying to introduce briefly PIANC and what we are doing with PIANC and what does it mean. I try to make it brief and concise. PIANC, probably you might know, is a worldwide network of professionals and who is providing expert advice on cost-effective and sustainable waterborne infrastructure. That is, ports, maritime structures, and coastal areas. These are the areas that PIANC is, working. You might, ask that question, how that PIANC, come to the board. It has been established in 1885, and it was the Waterborne Association, and the headquarters is in Belgium. And that's is up and running for 140 years. So it's one of the oldest associations specialized in waterborne infrastructure, waterborne transport-related infrastructure, if I want to say it correctly. So the question is, what PIANC does? Actually, the main core of business of PIANC is delivering high-quality technical reports. If you have got the time to tune into the PIANC website, the main organization, you probably have noticed there are more than 150, 160 technical reports and guidance related to maritime transportation and waterborne infrastructure. So these are the main core and business of the PIANC, and we are trying to support as part of the international commission and working group. So this is the main part of the PIANC. The second part is a network of international experts, connecting all of the experts together worldwide and sharing the knowledge. That's the second part. And also supporting young professionals and countries in transition is the third aim of the PIANC. And also, we are trying to keep the network connected through the international and also regional chapters. I can say PIANC remains the leading international source of waterborne transport-related information in 21st century after 140 years activity in that field. And this is pretty, awesome. So why to join PIANC? There are a couple of reasons. You have seen the leaflets on your desk, and also there's a couple of points notice on the flyer as well, on the banner. I want to just make a couple of highlights. The first things that I said is getting access to all of these advanced technologies being developed. And as I said, 150-60 publication related to waterborne infrastructure is amazing. And it's not only the publication, it's the working groups that's reviewing and also updating or adding additional publication. At every time we got 50 working groups online and active working in one subject. So that's how the system works, and it's a knowledge sharing between all of the communities across the world. Addressing the climate change is the pretty interesting issue regarding how we are going to address the climate change, as well as while we are developing the infrastructure from time to time. And also team up with decision makers. That's a pretty good platform to team up with the key decision makers across the area, across the region, and also internationally. And also supporting young professional community. This is what we are doing, and that's the reason we are in Queensland University today. In terms of the demography of the members, I can say 43 qualifying members are existed with PIANC. 27 out of that members have a national section. Australia is one of them and is one of the most active national section of the PIANC. PIANC internationally got 1,800 individual members, 500 corporate members, including port authorities, private sectors, universities, and also consultant engineers and contractors. In addition to that, PIANC got 12 platinum partners that they are supporting PIANC programs and activities. This is the map showing the location of the members and type of the members that we have. You can go to the website and get more details. PIANC A&NZ, as I said, is one of the most active national section of the PIANC. Currently, we got 180 individual members, 50 student members, and more than 95 corporate members. The corporate members are almost all of the port authorities across Australia. We got professional associations like universities and research centers as a member, and also we got public and private sectors, including various famous consultant engineer and contractors as part of PIANC. And the data is accurate as 31st March 2023. PIANC is led by a very active board member. They got a regular meeting addressing all of the subjects, and the chair of PIANC currently is Luke Campbell, and he is a director of WGA. And this is the photos of some of the boards of the PIANC. PIANC organized and also co-organized 2 big conferences in Australia. That's the regional activity that PIANC involved. The first one is PIANC APAC 2022. You probably have seen or probably attended the last APAC in 2022 in Melbourne. That was one of the biggest event after the pandemic, and the turnouts in my understanding was around 500 people. It was pretty amazing, and the topics that addressed during that event, it was pretty amazing too. The other one, which is the next Coast and Ports 2023, is coming up in August in Sunshine Coast in Queensland. It's just not far from here. is a collaboration between Engineering Australia and also PIANC. So it's 50% collaboration. It's a good collaboration between two engineering body addressing coastal and port subjects. It has various subjects, and also our chapter is organizing a pre-workshop. It's going to be a day and a half days workshop before the conference, and we are going to cover a special area, and you can get the details shortly via the website. As I mentioned, PIANC A&NZ regional chapter, they got 7 different sections. The northern chapters covers Queensland and Northern Territory. It has been marked as red. You can see it, and you can see the other regional chapters working in different area. New Zealand is a separate chapter, and also Tasmania just separated recently from Victoria as an individual chapter. The chapters are independent in terms of the governance. They have their own leadership committee. In Northern chapter, we got a leadership committee around 12 members, and some of them they are among you guys. You can network with them and get more information after the event. What we organize and holding local events like the one that we organized today with the collaboration of University of Queensland, and I'm pretty thankful to Professor Tom Baldock for that opportunity, for giving us that opportunity to organize that event. Also, we are supporting mentoring young professionals locally, and also we are contributing to the body of knowledge and technical reports. The upcoming events that we already organized is a Darwin networking event coming up in 17 May. That's in Darwin, Northern Territory. Coast and Ports 2023 workshop. That's in 14 to 15 August, Sunshine Coast. And that's a workshop for the conference. And also the technical topics for ports of Townsville. This is related to the development of the port, as well as port tour. That's going to happen in 5th of October 2023. So if anybody interested to come up to Townsville, we would be very delighted to have you guys there. Also, we do have mentoring program. And last year, we managed to connected to 32 participants, and we got 22 mentors to mentoring 32 mentees. And all of our mentors from one of the leading organizations that you can see on the right hand side. So the mentoring program is pretty good, because the young professional, they can get their hands on the topics of the waterborne infrastructure that they might be interested to carry on in future, and what they are going to do. There are 4 awards. I'm not going to go to the details. You can go to the website and see the details. But what I'm going to highlight today, most of these awards are for young professionals under age 40. So if you are interested, you can join PIANC and also apply for one of these awards. And these awards are coming from the international organization certified by PIANC A&NZ national section as well. The technical reports are distributed in 4 commissions: the MARCOM, INCOM, RECCOM, and Environmental Commission. So there are 4 different, commissions within PIANC. They are developing reports. They are state-of-the-art guidance, and they are the most up-to-date guidelines and technical reports regarding waterborne transport infrastructure internationally. And if you guys have been working within the consultant engineer, you have been seeing these kind of reports, and you have used it for, from time to time. And they are all free for all PIANC members. And what I'm going to highlight for students that they are interested to join PIANC, because it is free for students, as long as they have been registered within the university, so they can just tune to PIANC and get access to these 150 reports online free. I'm just passing these ones. That was the highlights, and how you're going to connect to PIANC and get connected. You can go to our website. You can tune into our social media like LinkedIn, Twitter, and YouTube, and or you can talk to one of our leadership committee members here to see how you can get connected. These are the information. I guess I leave that one after the session so we can talk more about it. The leaflets are there. You can get more information on the leaflets. And I guess I'm going to wrap up. That's it. Thank you very much for your attention.
Great, thanks for that, Sam. If anyone has any questions about anything that Sam's spoken about just before, then at the networking event afterwards is the best place to come and have a chat with Sam, myself. We've got quite a few of the committee members out here, Andrew, A&NZ, so just come and have a chat with us if you have any questions about that stuff. It's my great pleasure to welcome our first technical speaker for the evening. Professor Tom Baldock is the head of the School of Civil Engineering at the University of Queensland. His research is primarily focused in the field of coastal and ocean engineering, but also encompasses renewable energy and higher education. He has published over 120 journal papers and over 80 conference papers, and is one of the most published authors in the Journal of Coastal Engineering over the past decade. Tom will be presenting on the M4 wave energy conversion device located in Western Australia, and present on the civil engineering research themes that are currently offered at the University of Queensland. Welcome, Tom.
Okay, so good evening, everybody, and thank you very much for coming along today, and thanks to Sam and Jack for prompting us to host this meeting tonight. Something we should probably do a lot more of, but everything's very busy, but it's great to see so many people here, and also some of our current students and perhaps some of our former students as well. So look, I'd just like to again make an acknowledgement of country for the traditional owners and pay our respects to their ancestors, descendants, and their spiritual connections to the country. Okay, so look, I just wanted to run through some of our research themes in the school before I get on to the main topic of the proposal, but I'm mindful of time, so I'm going to be pretty quick. But of course, our mission is to educate our students and will enable them to create our future society in particular. Then we have a discovery mission as well, which is about the research side, which we're sort of talking about today in some respect, but also today is about bringing people together for the engagement mission of the university as well. So it'd be great to talk to people about those things later on. So our overall research themes within the school is perhaps captured by this, is adapting to climate futures, and that's really where all our research themes are trying to go. Whether it's coastal engineering or structural engineering, it's all about managing that aspect. So we work on a whole range of things, and we can start off with the natural systems that a lot of the groups in the schools work from coral reefs to water quality monitoring around the country. And then associated with that, of course, there's a lot of work done on starting to move into the real natural ecosystems themselves. Recovery of waste is a big theme in the school at the moment, and some of us trying to get into the renewable energy space as well, as we'll see tonight. I guess there's an underlying theme of all of that, and perhaps that's where civil engineering really starts out, is with protecting people and places from natural hazards around the world and providing sustainable urban societies and societies that are non-urban as well. So we have a whole range of aspects in that. There's a fire group here at UQ, which is fairly unique. So that gets involved in bushfires and things that perhaps is something we do at this institution that's not very common elsewhere. But there's a whole other aspect of coastal work in that too. And of course, part of that is maybe perhaps traditional civil engineering infrastructure like dams, protection against cyclones for buildings, but there's a lot of work going on in natural hazards around the world, in the Pacific in particular, to do with sea level rise on islands and tsunami risks too. So in terms of the structural side and the transport groups within the school, they're really working hard on that sustainable infrastructure. How do we get decarbonisation going properly? And there's hopefully some work that might come about that within the university soon associated with the Olympics. And of course, you're all working in that space in industry as well, and we're very keen to find out what's going on in industry on that space as well. Associated with that, there's a big push in the school with timber at the moment. We have a specialist timber hub here, and they're going to obviously contribute greatly to new structures that are moving towards net zero conditions. But there's a whole range of aspects on that, from offshore aquaculture looking at to reusable structures and deployable structures as well. We have a strong group in that field. And then associated with the transport group, there's a big push on digital design and technology and collecting all that big data associated with modern urban life and working out how to make predictive models for that, data analytics, et cetera, et cetera. So there's a very broad range of activities and research in the school. We're going to touch on a very small aspect of that today, but it is really focusing on that climate change adaptation. And some of that's obviously getting into robotic construction of temporary structures, but also trying to work that into more permanent structures as well, and things like folded structures. So we have many, many partners, and it's good to see some of those partners here tonight. So thanks very much for coming along. So I'll switch over to the other presentation, which hopefully won't be, is more on the main theme. And so firstly, this is not really my presentation at all. We're involved in this project on the M4 wave energy converter, but I've been waiting for a year for a PhD student to get a visa. They don't arrive actually till June, so I haven't yet done any significant work on this. So this is courtesy of Hugh Wolgamott at UWA and Brad Saunders at BMT, and is a presentation that a cut down version of a presentation that was given at the recent AOG over in Perth. So the M4 project is called M4. M4 stands for a multi-mode wave energy converter, which was actually developed by Professor Peter Stansby, who is at the University of Manchester. And that device was proposed essentially as a trial device within this CRC project from the CRC Blue Economy. So there's a whole bunch of researchers on that. So we're included. Dr. Remo Kosu is one of the lead of the environmental part of that program. There's a lot of work through University of Tasmania and UWA, particularly for this project. There's a whole range of other partners as well in the CRC. And BMT are doing most of the engineering work that you'll see I'm talking about later on. And then this is going in offshore in WA with the help of the Albany and WA governments. So hopefully you can see roughly how it works. So this is rather nice wave conditions for this particular device, but essentially it's got a forward float here with the two central floats, and then the power takeoff unit is sitting there in the middle, and the rear float is the largest float, and that gives you the most wave drag, so it keeps it in line with the waves. And you get both surge, heave motions out of that system in that combination of floats. So, of course, the main issue with all the wave energy devices, they all work great in unidirectional monochromatic waves, and when you put them in multi-directional random waves, efficiency goes down. So that's the purpose of really of this trial off in UWA. So that's the device that's being tested at AMC at University of Tasmania there. There's been quite a lot of other tank testing of it in the UK as well. So look, so why did they choose M4 for that particular project as a demonstration? And this is a demonstration project at a small scale. It supposedly has a good optimization over a broad range of wave conditions for a lifetime cost of electricity. And it's supposed to be, so far, at least according to numerical modeling and the testing being done so far, as good a device as any. But again, people have been claiming their wave energy devices since 1970 are optimized, and yet we don't have many in the ocean. So that's a key aspect. Survivability of devices is a big aspect, and again, this device has been tested in fairly extreme waves, and the key thing is that if the waves get too big, the floats just start to submerge and you don't start putting more and more forces into the device, so it becomes safe from that perspective. The power takeoff unit is above the water surface for maintenance purposes. They're not all like that, and obviously, it's a floating model rather than fixed inside a structure. A relatively easy mooring system, quite simple overall construction and design in terms of operation. There's nothing too much to go wrong in the system. We've seen some failures of wave energy devices, both through structural failure, but also then quite complicated devices put out in the ocean. They just haven't functioned as expected. There's a lot of publications on this device from Peter Sandsby if you want to read more about it. Some of them are very technical if you're really into your technical side of numerical modelling, especially fluid structure interaction. Peter's done a lot of work on that, and it's been quite well supported by the UK Research Council too. So it's going in off at Albany, which is perhaps in the future where the Red Cross here is a major resource site, but this device is not actually going off there because it's a trial device, and it's actually going off on a much more sheltered site on this side of that part of near Albany, where the wave climate is much more restricted by a weather window, and you don't get the full Southern Ocean coming in there. So that's the reason for choosing that site, and Albany is a bit of a chosen hub for the West Australian government, where they hope to kick off wave energy in the future if things work out. There's some wind farms there already on that coastline, so there is a grid connection and things they can tap into there if they want. And there's also quite a lot of interest in doing aquaculture down there too. So the BMT are doing a lot of the design work for this, which is still in hand, and there's most of the expenditure of the project is on that those costs of actually getting a real working device out in the ocean. So it's about 4 million all up with some in kind. Some of that's coming from the CRC, some of it's coming from the West Australian government, and some kicked in by University of Western Australia. I don't know whether this timeline is still directly on track, but there's supposedly coming later this year some initial deployments, and then that's hopefully going to stay in there for a whole year to collect data on that basis. I think there was some mention of possibly coming out over the winter period because they weren't 100% sure on whether it would survive in that time, and it then might go back again in calmer weather. So interesting to see how that behaves. So look, that wave climate is very sheltered compared to the main Southern Ocean. So most of the waves are, down here at sort of 1 metre, and you get a few waves up around the 3 metre mark. But of course, on the other side of the headland there, things are much, much larger than that. So there's an aperture window there that swell can come into. There's been monitoring at that site for a while now there that's going into the design by BMT. So that data has already been collected, but there's quite a lot of sheltering at that site. In terms of a few more details, so you can see that there is the shelter from the main Southern Ocean waves is pretty well sheltered, but you can get those easterly waves coming in there, and it'll be interesting to see, depending on the wave climate that occurs during the deployment, how that actually works out in practice. I'm not sure exactly what the design wave condition they've gone for the extreme here, and how much work's gone into saying, okay, well, we think this is, over the deployment window, that's really the maximum likely wave height, and what sort of risk appetite's been taken in that design. It's possible that if they really get an unexpected weather condition coming in, they might be able to move it closer into a more sheltered location, closer to the shore in that embankment. So BMT are leading that design, so they're building the structural models, and the structural engineers would know far more about this than I would, but it's coming along quite nicely, I think, in that respect. There's going to be some further tank testing of the modelling, I think, before it actually goes out there. But it's certainly an interesting structure and fairly unique in terms of an offshore deployment in that respect to work on for BMT. So it looks a bit like that in the cutaway motion, and then the whole point of this system with the 3 floats is that the back float being the largest, and that seems to be a patentable idea to keep it in line with the wave direction. So the most drag will be on that back float, and that means that you don't have to worry about sorting out the wave direction. It's interesting to us why you've only got a one float with a moving arm and you don't have a power takeoff unit, say, associated with the front float, because obviously there could be motion there as well. So our particular work on the project is to try and see whether we can do any further optimization of that device compared to the current proposal. It won't feed into the device that's going out in the ocean, that's being designed now and built, but we've got 3 years to see whether or not we can make any further improvements in that system. That could be things to do with the way the floats are organised, the shape of the floats. Should there be more trailing floats? Should you try and take power off in more ways, etc., etc. So that's our part of the project, which we'll kick off in about June this year. So just a sense of scale. So it's about 24 metres overall length in the prototype model. It's going to be 9 metres or 10 metres wide and about sort of 5 metres maximum overall height. And there's quite a big range of the float motion from in extreme wave conditions. Seems to be possible in the design. So that'll be interesting to see whether they get any waves that give you that sort of range of motions in that case. So look, reasonably, reasonable size to deal with a prototype, but not a trivial size model that you'd get within tank testing. So it is really going to scale things up for those tests. So that's the float dimensions. The forward float's 2 metres, the middle float's 2.5, and the rear one is 3.5 metre diameter with a draft of about 3.3 metres. So a significant structure to put out there and test on that basis. So the power takeoff, that's going to be a fairly standard design in reality, but they've decided not to go for an actual power takeoff unit for the trial, take that power to the shore. So they're going to be dissipating all the energy generated on the device itself and then measuring that. There will be 2 power takeoff units in the centre, and I think a fairly standard set of gearboxes and power electronics for that case. I don't think this device is a bit different from some of the wave energy devices. I haven't seen anything that much about optimization through latching and those sorts of things, about controlling the motion to try and improve the energy efficiency. Don't think they're trying to control the floats and the mechanics in that way, which a lot of devices actually do that. Okay. So what sort of power are you expecting to get? Well, if you compare this with your solar power on your roof, it's not that much, and that's one of the things about wave energy. Everybody says, oh, there's a huge amount of energy in the waves, but actually the density is not that great. So for typical waves here, well, maybe it's 1 to 2 kilowatts, and maybe you'll get 5 to 10 if they get the wave conditions that they hope to achieve. But your solar system on your roof or many solar systems will be getting up to the 6 kilowatts without any difficulty. So it's quite a big structure, and it's only producing that sort of amount of power. So you have to keep that in mind, and perhaps that is why wave energy hasn't taken off as much as we would like to expect, or at least it's been worked on for 50 years and there's not that many. I actually been trying to find actual devices that are properly connected to the grid. There's lots of people that claim they are, but when you go and look closely, there don't seem to be actually that many devices connected to the grid around the world. Of course, there's a whole load of issues associated with permitting, because this is now a real structure going out in the real environment, and then that's something that us as academics don't deal with much. And again, you have a lot more expertise in those sorts of issues than we do, and I think those have all been pretty much agreed and signed off by now. So those are a lot of issues, and one part of the CRC is not directly associated with this project, but other parts of the CRC are really looking at regulations for the offshore environment for these sorts of structures, which still seem to be a bit of development required. So there's 43 partners overall in the CRC. Only some of those are associated with this project directly. And again, the main ones here would be UTAS and BMT. But TASL is probably the main funder of the CRC as a whole, and money in from CSRO as well. The others are all in-kind partners and smaller bespoke input into particular projects. Okay, so I'm happy to take some questions there. I'll do my best to try and answer them if there are any. I'll leave that playing while those go on. But perhaps in a couple of years, if we have another one of these sessions, we can give an update to what we've actually found out so far. Thanks very much. Yep.
I just wondered if there's any collaborations with
I don't think there is directly in this project, but I'm sure that Peter Stansby has done in the past because he's obviously based in the UK. I haven't heard of this directly through that. I know there's a lot of work going on up there, and actually my brother does some work up there in the UK, interestingly enough, on mostly on tidal stuff. Yeah. So that's a very challenging environment to work in, and I think there was a wave swing device or went up there, but I'm not sure it's still in the water. So quite what happened to that, I'm not sure. But yeah, so this is a fairly sheltered site compared to that situation. Yeah, but it'd be good to chat about what you were doing up there.
Yeah. I've got a question from online for you, Tom. Thanks for the presentation, very interesting. How will the structure be anchored?
Okay, so I don't know they fully decided that yet, but it is a single point mooring. So there's simply, I imagine I don't know if they've decided to go for a foundational, screw type anchor or just a weight on the bottom. Then there's a float up to the top, and then there's a single line from that to the front of the device, and that seems to be the approach for that. So, but whether that design is fully done yet, I'm not sure.
Yeah, okay, thanks.
Like small energy generation, 1 to 2 kilowatts or something, you said, what's the gap in the market for this compared to like wind, offshore wind, that for the same chunk of offshore area you could probably...
Well, look, so that's really why this is the demonstration project, and I don't know if I'm best to answer that. I mean, the offshore wind is what, 10 megawatt turbines or something at the moment. Okay, so, and that's just one of them, and a 10 megawatt device that would do that of this is an awful lot bigger and possibly much more expensive than that at the moment. So that's really the challenge that anyone working in the wave energy space is facing. Can it be competitive with offshore wind? If you read Peter Stansby's papers, they claim that it can be, but there's a lot of assumptions in that. And again, those claims have been made for many years about wave energy devices. So we'll wait and see whether that materializes or not. But look, there is, I mean, I suppose really that, the claim to fame is that perhaps there's a more reliable source there than the wind. So, there's possibly a base load on that basis. But yeah, again, it's questionable. Okay, so perhaps mindful of time, but also I would just say that when saying, if I don't at the end, if you're sticking around for the drinks and a bit of snacks at the end, we've got to move over to the Advanced Engineering building, which has just come out of here, essentially go left and keep going straight and then into the big building across the road. And we're up on the 5th floor there, and there's some tea and coffee and some light snacks to do. So hopefully you can stick around for that afterwards. Okay, thank you very much.
Great, thank you, Tom. It's my pleasure to introduce our second speaker for this evening. Remo has over 15 years of research experience in water engineering and joins the University of Queensland School of Civil Engineering in 2016. Remo's research projects spans over a range of topics, including marine renewable energy, hydrodynamics in coastal areas, sediment transport processes, seafloor mapping, and environmental engineering. Remo started his professional career as a research associate at the Hanover University in Germany and has since gone on to hold several key positions at the University of Toronto and the Australian Maritime College down at the University of Tasmania. Remo's presentation will focus on the wave swell oscillating water column device that's currently off King Island. Welcome.
Thank you. It's just the wrong presentation.
Oh, it's the wrong one.
Change this a little bit. Have you got it in the... should be. In.
All right, so good evening, everyone, and sorry about the mishap. I was tinkering with the presentations a little bit, and that's, I think, the latest version. So I call this presentation From Cradle to Demonstration. So and that is actually where wave energy, we just talked about it, is at the moment. So most of the devices that are in the water are not really at large scale, but at demonstration scale. And I just want to focus on one, let's call it successful project down in King Island. So, and that is the OWC, so the oscillating water column. And I'll explain that technology in a second. So I wasn't really sure about the audience today. So, and we just talked about wind and wave. So wave energy obviously comes from wind energy, and wind energy actually comes from solar radiation or the differential heating of the atmosphere. The funny fact about wave energy is that it actually intensifies, so it's much more powerful than solar or wind energy. So just by its nature, so because it's in a denser medium. And when we talk about wave energy conversion systems, we're just really looking at harnessing waves from wind and not the long crested or longer waves like the tides and also tsunamis. So in terms of the power resource, wave energy, so that's just the global scale, and that's a big number. So 2 billion kilowatt that are in the ocean. And what you can probably see here is that the roaring 40s in the south. So thanks to the fact that we have little landmass in the southern hemisphere and a lot of landmass in the northern hemisphere. So the southern hemisphere and especially Australia are actually quite lucky in terms of having this resource. So if I zoom in a little bit here on Australia, I think Australia's fraction of this 2 billion is about 0.2 billion kilowatt. Here along the southern coast and also along WA, so that's where the M4 project is located. So they picked, obviously, that's what Tom's slide showed, the world-class resource. And those 0.2 billion kilowatt, they still amount to, I think, 7 times what Australia actually needs in terms of resource. So it's a bit of a tricky situation. We know it's out there, the energy, but how to harness it, that's the big problem. And the other diagram here shows, again, that how lucky actually we are here in the southern hemisphere. So the blue colors indicate they have quite a low coefficient of variance, whilst a lot of projects or resources here in Europe, that's the green color, they have a slightly higher coefficient. That means that between the mean wave height and the extreme wave heights, so the variance is actually quite little in Australia, whilst in Europe it's much larger. So and this variance correlates with the costs. So you actually have to design the devices a bit differently if they are subjected to these extreme wave loads. Okay, so opportunities for wave energy, lots of them. Just be mindful of time. So that's highlighted here. I think the best option at the moment for wave energy conversion is really looking at the island and coastal communities and the off-grid operation. So just having devices that harness not much, but enough for these remote or autonomous islands. So some snapshots outside of Australia. So we talked a little bit about the M4 device. So, and the wave piston device here, that's designed by a Danish company, and it's currently deployed in the Canary Islands. So that is a system that pushes basically from the horizontal motion. There's just plates in the water, and they push water into a pipe. So they just increase the pressure in the pipe, and it can either spin a turbine or is used for desalination. Similar to the other company here, Resolute Marine, that's a US company. They're just trialing their technique that's kind of a bobbing piston again, also pressurizes the water and can drive a turbine or a desalination. And that's currently tested off the coast of Africa and the Cape Verde Islands. And Penghu, that's a device, I think that's designed and deployed in China, combined with an aquaculture facility. And the big one here that has been funded by Horizon 2020 in Europe. Musica, that stands for, let me again see if I can get that together. Musica is the multi-use of space for island clean autonomy. So again, it's a system that is designed to support offshore islands. Right? So, and just either give guidance, power, or water, right? And can be also in combination here with aquaculture, for instance. It's a floating device. So that is again they funded this project and it's in its trial stage. I'm going to talk about that in a second. So I want to focus, and I think we've seen this device now in a few slides, on the oscillating water column in King Island. So we call it the UniWave 200 because it's designed to produce about 200 kilowatts, so a bit more than what the M4 does. And I underscored here a few of those words, so range of condition, generating electricity, demonstrating the unique methodology, and also confirming its potential. And these are all keywords that actually come up when you look at the technology readiness or technology readiness levels. So there's 9 of them, and we're going to start here from the bottom. So the basic principles, and then this just goes on and on. So to the latest stage, so wave energy conversion at the moment, yeah, we don't really have any that has really passed 6 or 7 at the moment. So that's the problem with the wave energy conversion system. So again, we know the resources out there, but to harness it is just the bigger problem. So what I want to now focus on the next slide is basically the different steps that this wave energy conversion system down in King Island has gone through. So from the basic principles to the lab scaling, and then also finally putting actually a device in the water that is still a pilot scale, but is able to harness up to 200 kilowatts. So Waste Energy is a Melbourne-based company, and they, I think, have about now 25, 30 years of experience. That was their what they call the light bulb moment, just actually looking at a blowhole and trying to use this technology to create or harness energy from the waves. So it's the first unidirectional airflow system. On the next slide, I'll show you how that actually works. And the big advantage compared to all other wave energy devices is that it has no moving parts in the water. So it is actually quite resilient to the wave attack. And in terms of survivability in storms, this device definitely has a big advantage in that regard. And also as an additional benefit, those devices can also be used to be integrated into breakwaters or just stopping basically the coastal erosion as being kind of an artificial reef. So that's just kind of a slice through the device. So it has an opening towards the sea. So the waves actually come in here, and it has a hollow chamber. So the water level here rises and falls. So and on the upstroke, so when the air is actually compressed, it escapes here through the valves. And on the downstroke, so when the water level decreases in the chamber, these valves close, and so that the air is sucked in to the turbine, and that really powers and spins the turbine. That's what the previous slide actually meant with unidirectional. And apparently that's better because a unidirectional turbine is more robust than a bidirectional one. So when you look at how the water level rises and falls inside the chamber, naturally there should be, from an engineering perspective, a few things should come to mind. Resonance. So obviously we need a good understanding of the wave climate in order to be able to deploy this device. And we also should understand a bit more about the water depth and also from what angle the waves actually flow or come into the structure. So we had the model test basin in the previous presentation from Tom already. So the model test basin down in Tasmania. So they were actually tasked by Wavespell to do the first, I think that was in 2016, starting with the first, well, very basic actually design of this device, just looking at loads and forces, the pressure flow, and also the valve efficiency and durability. So that's been tested in at the model scale. And the next slide here on the y-axis shows the efficiency, and on the x-axis we have the wave period, so the frequency. Again, that is quite important to actually drive this whole system, and the variation in the wave climates and the wave height. So parameters here are the wave frequency and the wave height that have been modeled. And what you want to take away here is that there's obviously a sweet spot. So in terms of the frequency, whilst the wave height maybe doesn't have as much impact, but it's the frequency plus actually then the wave height that gives you this superior efficiency. And these has been tested lab scale and regular waves. We also have that for irregular waves. For irregular waves, it doesn't look as good, but it's still actually quite efficient. It's one of the most efficient conversion systems so far. So, and that's where actually now UQ and my research comes into play here. So we have been tasked by Wavespell to look at spots where this device can be deployed. So on the parameters were obviously the wave climate, so the wave direction, the wave frequency, and also the wave height, but also the water depth and also the slope of the seafloor. So the first survey we actually did on the west coast of Tasmania, and it took us about 4 months to find a time window of just 2 or 3 days where we could actually go out and do a survey. So the west coast, and remember the roaring 40s and all the wave climate that actually hits Australia from the west is pretty powerful. So for a test site, that wasn't that good. So then the plan actually shifted to the east side. Oops.
Come up here.
The plan shifted to the east side. So since 2018, we have been surveying the area here near Grassy on the southeast coast of King Island, and again finding this really the sweet spot of with the correct water depth and also getting more information about the wave climate. So I'm not going into the different survey methods. I think that would be a bit too much at this stage. Happy to answer questions later. But just here some impressions. So we actually did some underwater piston coring, just with dive operations, and just looking at how much sand is there. So how thick is the sand layer? So that was another parameter. So they wanted to have at least 1 meter of sand. The bathymetry. So we did measure the seafloor and the sea slope. Here's a picture of the cores that we took at different locations just to confirm how much sand is actually in the water, and with some sub-bottom profiling. So this picture here shows the tracks of our vessel, and that's the profiles from the sub-bottom, just looking at the bedrock and the sand coverage on top of it. A little side effect was a study. So we used actually different instruments to measure the wave climate. So these instruments here, they operate on acoustic signals, whilst the wave-rider buoy just operates on displacements. And we were just able to compare different methods and the different instruments. They all actually came back with very good agreement. So this is the wave height here between 0.5 and usually 2 meters. So that is the typical wave climate in Grassy. The wave period is pretty constant, around 10 to 12 seconds. And more importantly for wave swell was also to see that the direction. So the wave attack is also fairly uniform, just from the south, just 180 degrees from the south. So it's a pretty good spot in terms of the wave climate, because it's quite constant. Why am I showing this slide? Just in terms of dimensions. So I think I just forgot to actually give you the dimensions, but from bottom to top, that's about 15 meters. So that's quite a large structure. And from the rear to the front, it's about 25, 26 meters in length. So, and you can also see that the bottom here is adjusted to the slope. So, and only once we actually had the slope of the seabed, we could, and this bottom part could be built accordingly. So this green area here, that's the L shape. So that's really the hollow chamber, whilst just for stability, there's ballast tanks, and the electrical room that is above the sea level again. So all the moving parts, the turbine that sits in the superstructure, that's very protected from the waves and the wave attack. So in, I think in 2019, they actually began building the structure in Launceston, and then it was towed out to a different port where it was finalized, where the superstructure was added, and then the whole structure in December, January, and then January 2022, so last year, it was towed out to Grassy, to its deployment site. Was fairly calm weather, so that was good. And it took them about 2 days just to get from the port in Bell Bay to Grassy. So ever since then, there have been monitoring and testing. So on average, it puts out about 50 kilowatts, but in a wave climate between 0.5 meters and 1.9 meters. The peak efficiency is 76%, which is really good for a wave energy conversion system. On average, we're just under 50, which is still okay. So I think Waveswell is quite happy with the performance. So ongoing maintenance, that is a big learning curve, I think, for these devices, because if you put them on sand, they tend to scour. Right? So they tend to be scouring. Again, if the water depth, or so if it actually settles, that changes a little bit the water depth in the structure and its efficiency. So again, they needed to do some scour protection measures. So Tom and I had the luck just to have a very bright student who did some actually testing here at UQ with the structure. First, just the basic structure as a block, but then with the pontoons as well. So just looking at how actually, where does erosion, where does sedimentation actually occurs with the constant wave attack and the sediment movement around the structure. So that's something we actually did trial, and it was, I think, the first study ever that has been done in combination with the wave energy conversion system that has been deployed, just getting real data of the sedimentation and being actually able to replicate it in the lab. So yeah, there's a lot of, there's a lot of lessons to be learned from deploying this device. Again, that's the pilot stage. So we're at the technology readiness level 5. So to be fully commercialized, we have to go all the way to 9. So that's just looking at the time. So that's my last slide. Actually, just I want to really mention that. So all the development from basically the basic idea, just having this idea of a blowhole and using that to harness the energy, to the pilot study. So that basically took, well, let's say lab scale. So just the basic principles to the pilot scale, that it took about 5 years. So from 2016 to well, 2022, then at that time the device was deployed. It still actually is in the water, so they're still monitoring it. But these levels between 1 and 5, so at the lab scale, even at the demonstration scale. So this is really, I think, the realm where industry and university can really work well together. So in terms of this research, in terms of trialing, in terms of changing things, once it gets to the large scale and to the commissioning. So that's when, yeah, really need the big bucks and investors. And at that stage, usually things don't change, they just get bigger. So that's just more risk management. So I think that's the nice thing about well, the early stages of these projects, because they allow for, like I said, very interesting collaborations between industry and academia in terms of education, in terms of innovation, and yeah, what it also says here, our social responsibility. So wave energy is a very, well, great resource. It's just very hard to capture. And there will be lots of research needs to be done to be actually able to harness this energy. So I'll just leave you with that quote, which I found somewhere. But like I said, it really requires a lot of collaboration to make the next step and having actually more of these pilot projects in the water. And at some point, maybe in 10 years' time, maybe in 15 years' time, I'd say we will be able to probably harness a bit more than what we do at the moment. Yeah, so that's it from me.
Thank you for that, Ramo. That was a great presentation. I really enjoyed watching that. We have some time for a couple of quick questions, and then we'll try and get on with the last presentation, just because we're running behind. So.
Just a quick question. Did you consider to have a double turbine, one for the in and one for the outgoing movement? And what did that do, if you consider it in your concept, what did that do for the efficiency?
That's the Wavesport Energies concept. So they usually, I think every time they present, they get asked that question. They claim, and I can't really say yes or no to that. So, but they claim they get a much better efficiency by just having it in one direction because the parts don't break down that much. They're not used in both directions that often. So I think from a robustness point of view, that's better. If you look at the tests and if you look at the pneumatic efficiency, yeah, the numbers are just there. So they just can constantly actually generate this power. So.
Yeah, you have two turbines, not one.
Two turbines. So
out, but takes in, and the other one that takes the air out. So
yeah.
Turbines, both as efficient as you could do, but making use of the movement up as well as the movement down.
Yeah, no, that's that. I would probably put that question to them. So I don't know if that's something they have really thought about or not, but I'm pretty sure they have because they've been working on this concept for 25 years. So.
Was there a question over there?
So there's a very similar device to this that was on the Isle of Islay in Scotland called the Limpet, which was a wave gen device that was in commercial, actually was running commercially into the Scottish grid. And I just wondered if you'd looked it up and basically, I think that this one's multi-directional, and I'm not sure the one in Scotland is, but it went out of business, I think, about, I'd say maybe 14, 15 years ago. But it's worthwhile having a look up because it was a similar setup with the turbine that pushes the wave up in full. And it's probably worthwhile having a look at that for comparison. Yeah, I don't know if you already have, but yeah.
One. Oh. I got. Oh, yeah.
think to get this commercially viable, you need to scale it up one way or another, because I mean, you say 50 kilowatt, that's not a lot. I just wonder if you make the analogy with the big offshore wind farms, scaling up there means bigger turbines. What does scaling up mean here? Because the wave height doesn't change, it doesn't get bigger.
Yeah.
Unless you put it in bigger wave areas, but what does scaling up mean for a device like this?
Yeah, no, it's a good point. So the next step, so that's and I think they actually scaled back from that. So the first site we actually surveyed in King Island on the west coast was in 10 meters of water. So this instrument sits in 5 meters of water. So it was from a dimensional point of view, the structure itself is maybe a bit higher, and the chamber is a bit bigger. But it will deliver up to 1 megawatt, so 5 times what this device can do at the moment. It's just making it slightly bigger in terms of the footprint. I think that's 20 by 30 meters, the footprint that we're looking at on the west coast, and there was a design for a 1 megawatt structure. Just required larger waves and just bigger water depth.
Thank you. All right, I think we'll get on to the next presentation. Thank you for that, Ryan. That was great. So to introduce our final speaker for this evening, Tara is an experienced environmental resource lawyer and project director with over 15 years experience in delivering significant energy, construction, infrastructure and resource projects. As the energy sector lead for WSP in Australia, Tara supports clients and the community to transition to a low carbon future with a focus on emerging energy markets, including offshore wind and pumped hydro storage. Tara has previously worked with the government clients around Australia to develop and implement new legislation to support large-scale transition initiatives. Welcome, Tara.
Thank you, Jack, and thank you so much for the invitation to speak tonight. I have to say 2 things are jumping out to me immediately. Firstly, I'm very much outnumbered by engineering experience at the moment, so please be kind. Any detailed engineering questions I'm going to take on notice and refer back to the very experienced engineers that I have working in the organisation with me. And secondly, I'm also conscious that I'm the only one standing between you and drinks and snacks. So I will try to keep this concise, but very passionate about this topic. So sometimes I do tend to go on a little bit. Just like to extend my acknowledgement of country, similar to our other presenters tonight. So I'd like to pay my respects to elders past, present and emerging. I'm in a very fortunate position that I've been able to focus my career around renewable energy and the energy transition, and it's a great time to be in this business. Some of you may have seen this before, but Australia has made some fairly ambitious commitments around where we want to see ourselves, particularly in the next 10 years, as far as renewable energy is concerned and net zero. But I think it's fair to say that the scale of the change that we're talking about is unprecedented, both for us here, but also globally as well. The amount of new generation that we need to bring online, the amount of new energy storage that we need to bring online, particularly in the next 10 years, is unprecedented. And therefore, I think there's a real focus at the moment at looking on where is the biggest bang for our buck going to come from. And that's where technologies like offshore wind, for example, come into play. Another thing that really stands out for me at the moment with a lot of our, particularly our forecast modelling, is we are really focusing on domestic demand at the moment. So what is it going to take to transition Australia from predominantly fossil fuels across to renewable energy? That doesn't take into account some of the ambition that we're starting to see around in Australia becoming a net exporter of renewable energy as well. So if we try to bring things like hydrogen into the mix and some of these other technologies where we want to be able to export our resources as far as renewables are concerned, this picture changes even more, and the amount of generation and storage we need to bring on to manage that becomes even more important as well. So I think that's why we're seeing such a focus on offshore wind at the moment, and particularly in the last 12 months. This is really taking off as a new industry. I guess similar to what we were talking, what some of the other presenters have been talking about tonight as well around the wave energy resources that we have. You're probably aware that our wind resources as well in the offshore space are also world class. And certainly when I started getting into this industry, it really surprised me to know that our wind resources are actually better or stronger than what we see in Europe, which is sort of synonymous with the offshore wind industry. So the fact that particularly around the coast down in Victoria, Tasmania, Western Australia, for example, we do have these wind resources that justify the development of these gigawatt scale farms. I am a proud Queenslander, as much as it pains me to admit it. It's just not that great here. So unfortunately, the opportunity for us to develop offshore wind off the coast of Queensland is significantly more challenging and doesn't quite stack up to the same extent as it does in the southern states. But it doesn't mean there isn't a fantastic opportunity for our engineers and scientists and all different parts of the industry to get involved in these projects as well. I think in addition to having a really fantastic wind resource, there's some other key factors which are really driving the development of offshore wind at the moment. And one of that is around onshore constraints. We are seeing an increasing amount of pushback from communities and other stakeholders. They don't necessarily want onshore wind farms in their backyard. They don't necessarily want solar in their backyard, let alone big energy transmission lines as well. So there is something very powerful at the moment around putting something out of sight, out of mind. And we are seeing with the advances in offshore wind technology as well that we can put these farms a lot further offshore than even ones which are being developed 5 or 10 years ago, which is reducing that visual impact even more. I think, as I said, for me, minimising those offshore impacts is becoming increasingly important, and therefore the business case for offshore wind is becoming increasingly stronger as well. We've got a lot of demand, we've got great resources, and these projects make sense in some ways that onshore projects are really struggling with at the moment. So there's a lot of interest from developers, predominantly global developers who've built their track record in Europe, Asia and North America. At the moment, there's around 30 projects which have been announced publicly, but I can tell you there's probably 3 times that many projects which haven't been announced and which developers are biding their time as they're going through the regulatory process at the moment. So a lot of interest, particularly in New South Wales and Victoria. Some of the other states and areas haven't necessarily taken off to that same extent yet, but that will probably change as we move through the process as well. So you may be aware that until last year, in June, we didn't have any legislation that actually allowed us to develop offshore wind farms. And that's really been the key stumbling block, if you like, to getting this industry off the ground. When this legislation came in June of last year, the amount of interest and excitement from developers here and also developers overseas has been fantastic, and it's been the thing we've really been waiting for to be able to get this industry going. This framework is modelled very closely on the offshore oil and gas framework. So legislation that has been around for 20 or 30 years. A lot of the regulatory processes are the same. The regulator is the same. Anybody who's worked in offshore oil and gas has a potentially bright future in offshore wind here as well. So since June last year, clients and developers have really been working closely to understand this legislation and what that is going to mean for the development pipeline moving forward. With all of that being said, I'm painting a very positive picture. We are still very much at the early stage of this process. So the government is still working out where they want their offshore wind zones to be. And I should mention with this that this is Commonwealth legislation, so we are talking about Commonwealth waters. So looking at where the boundaries are going to be for these farms to be developed, and then also inviting applications for what are called feasibility licenses. So these are basically seabed licenses that will give developers the opportunity to then spend the next 5-7 years, for example, looking at feasibility studies and really proving up these projects to then move into construction and ultimately operation. So we are still very much at the beginning of this journey. And if we're talking about a 5 or 7 year feasibility stage and then a 2-3 year construction period, realistically, we're talking for these projects to be another 8-10 years off until we can actually see them out there and operating as well. So we do have a really long way to go in this process as well. In terms of the areas that the government is focusing on at the moment, the Gippsland area is the only one to date that has actually been declared. So that's the area predominantly on the western side, on the eastern side of Wilson's Promontory down there off the southern coast of Victoria, and a little bit of focus on the western side as well. One of the interesting things about this, I think it's the original draft zone that the government went out with was substantially larger than what's ultimately been declared and what proponents are going to be able to utilise. And that really does reflect community concerns and stakeholder concerns, particularly from that part of the world. So government is very conscious, I guess, of what the community thinks. And I think that's going to be an important consideration as we continue to move through this process as well. So the next zone that we're expecting to get formally declared is the Hunter Zone. So that's just off the coast of Newcastle. That's currently out for consultation at the moment and will hopefully get declared over the next couple of months. And then we're going to see similar processes happening for the Illawarra area, the Portland area off Victoria, northern Tasmania, and also the Perth-Bunbury area of Western Australia. So ultimately and realistically at this stage, those are going to be our offshore wind zones around the country. So a couple in Vic, one in Tasmania, 2 in New South Wales, and 1 in Western Australia. Picking an area is everything at the moment. This is something that we are supporting a lot of our clients with. You can have a maximum of up to 700 square kilometres, which is pretty substantial when you think about it. How you place that, how close you are to either existing infrastructure or other competitors, for example, is a really complicated game that everyone's working through at the moment, and something that I think will become particularly challenging when a government regulator is sitting there and they've got all of these competing applications. How they're going to work through that is going to be really interesting to see, I think. And there's going to be, unfortunately, a lot of disappointed developers out there who aren't going to be successful with their licence applications, unfortunately. How or where some of those successful proponents are going to come from is really driven by these criteria which are set out in the legislation. Yes, I'm referencing this. I'm a lawyer. I love this sort of stuff. But this is really what clients, when they're submitting these types of applications for their seabed licenses, these are the key considerations that they will be needing to demonstrate as part of their process. And the engineering support for this is a critical aspect of developing these projects and demonstrating that track record. So what we're sort of expecting is that this process is really going to favour those global offshore wind developers who've done this before in Europe and North America and Asia, and who can really demonstrate that strength of track record. They've developed 10, 20 projects, whatever that might look like, and they really understand and have really thought through how they're going to do this in Australia. And I think that's something that's really important to understand, and that there are some key differences between the Australian market and what has worked to date in particularly Europe. Our seabed conditions are quite different. The types of vessels that you will need to get involved here to do a lot of that work are very different. We don't necessarily have a lot of the port infrastructure yet that we're going to need to make this work. So understanding your supply chain, how you're going to bring these big projects together, is something that the proponents who really understand that are going to do, I think, much better than ones who don't necessarily have that breadth of experience before as well. So I'm assuming most people understand what an offshore wind farm is, so I won't spend a huge amount of time on this slide. But I guess for me, some of the farm itself is probably just one important component. understanding your cable route, understanding your offshore substations, understanding where your onshore substations are going to be, how you will connect into the grid, how your shore crossing will work, all those different pieces of the puzzle. Again, really important to have a good understanding of at the moment, and something that I think, again, the government is trying to sort of think through how they will want to coordinate some of these elements as well. So some governments, Victoria, for example, have said, you know what, we are going to coordinate all of the onshore parts of these projects. So you can just basically come and plug your wind farm into a grid connection point that we will provide for you. Other states, it's not yet really clear how that is going to work. There is so much opportunity in this space, and yes, I'm going to give a shameless plug for offshore wind recruitment at the moment, because to be honest, there is a lot of expertise that's needed, and if you look at where the market is globally, we don't have anywhere near enough people to really justify the demand that we're seeing at the moment. There's some resources overseas that have obviously developed their understanding and their experience in markets like the UK and Taiwan. Some of those people are heading back to Australia, but a lot of them are also getting sucked into all of the exciting developments which are happening in the United States and other markets as well. So for us, really being able to bring new resources in who can support with all of these key engineering aspects is absolutely critical. We're seeing a huge demand at the moment for support, particularly in ground engineering, so offshore and onshore geotechnics and geophysics. All of that work that you guys specialise in around coastal and sediment mobility is absolutely critical. Electrical engineering, both onshore and offshore, all of the work that's required around the port infrastructure as well. There's some key ports which have been identified in New South Wales and Victoria that are sort of expected to carry the load as far as these projects is concerned. But there's a significant amount of upgrade work that's going to be required as well. Offshore structures, onshore structures and civils, quality services, environmental, health and safety, wind resource assessment, the list really goes on. So for anyone, I guess, who's looking for an opportunity in this space, now is definitely the time. We're recruiting, other consulting firms are recruiting, clients are recruiting, government's recruiting, everybody's recruiting at the moment. If this is something that you're interested in, great, as I said at the beginning, great time to be involved in energy. And the scale of what we're trying to achieve can't be underestimated as well. So over the next 10 or 15 years, the future is really bright in this space, and it's only going to keep growing from strength to strength. I feel like I moved through that fairly quickly, so I think I've achieved one of my objectives. On that note, questions, comments?
The typical range, or not typical, the range of water depth in those. Do you have any idea of the water depth range in those areas?
I can't give you specific numbers, but what we're seeing at the moment is that for Gippsland, for example, tends to be somewhat shallower, so really supporting more of the traditional offshore wind technology, so fixed bottom structures, for example, whereas the areas, for example, off the coast of Newcastle, really, because of the water depths in that space, much deeper, it's really probably going to have to look more at a floating technology option. Realistically. Floating technology is obviously still fairly untried. It hasn't really been done at any scale yet anywhere. So that's going to be an interesting challenge for the Newcastle area to deploy that technology.
Just a general question. Who will be the authority that will coordinate all these activities? And will they go into the market to attract offshore knowledge and experience? And when do you envisage they will go into the market?
Really, really good question. I mentioned earlier in the presentation, what they've done is really modelled this framework off offshore oil and gas. So the regulators who operate in that space are taking this on as well. So NOPSEMA has a really strong role in this space. Other agencies like NOPTA, who are responsible for the actual titling parts, and then the Commonwealth Environment Departments as well. So those agencies have already been recruiting to build their in-house expertise, and will be continuing to recruit as well. It's very early days.
Just got a question online. Have the Australian government considered using a bidding method to assign developers to prime sites, or what's the process for that?
So the process at the moment that they're going to set out is a little bit a combination of what has sort of worked before globally. So I'll go back to this slide here. The way that it's going to work, everybody submits their application for their desired line in the sand, so to speak, and those applications are all compared against these criteria. If you've got competing applications, and one is more meritorious, if you like, than the other, then that person or that developer will succeed. If, however, they are found to be the same, so of equal merit, the way it's then going to work is that the government is going to gently encourage those developers to try and negotiate with each other and come to an agreement. In the very, I would imagine, rare circumstance that doesn't work, it's going to come down to money. So who can outbid each other? So I guess coming back to the question, where some markets overseas, that bidding process has been entirely financial and who can put the best offer, the Australian government is trying to sort of balance merit and technical experience and commercial capability with the ultimate financial aspects.
Thanks. Was there any other questions, or one more at the back?
Do you anticipate running afoul of the EPBC Act because of all the migratory species and other regulations around the coastal areas?
It's definitely going to be a process to work through that. Again, there is some precedent for it with all of the offshore oil and gas developments that have happened, but at the same time, these are very new projects, and the cumulative impacts of what we are talking about are not necessarily well understood. So this will potentially add a significant amount of time as proponents are working that through with regulators. There has been some discussion of doing a more cumulative assessment or a more strategic level assessment. So looking at the impact of having 10 offshore wind farms, for example, off the coast of Gippsland. But at this stage, it hasn't really been formalised in that respect. Each proponent is looking at the impacts of these projects on their own.
Great, thank you for that.
Thank you.
I'll wrap it up there. So that's all the presentations for this evening. Thank you to our presenters for taking the time out of your days to prepare those slides. That was awesome to see, and thank you to everyone that's turned up for the event tonight, and also those online. The presentation will be put online on the PIANC website for those that want to see it down the track. Now we'll do the next section of the evening, which is networking. So Tom will tell us where we're going for that next section.